Crystalline solids can be divided into molecular solids, ionic solids, and atomic solids. The molecular solids are made of molecules and they have low melting points. Example, ice. Ionic solids are made of cations and anions. The melting points are very high. An example is table salt. And the atomic solids are made of atoms. They can be non-bonded, metallic, or network covalent. The non-bonded are held together by dispersion forces that are very weak. They contain low melting points. An example is the solid xenon. The metallic ones are made of atoms joined together by metallic bonds. The melting point can be low or high. An example is gold. And the network covalent are made of atoms held together by covalent bonds. The melting points are very high. Example, silicon dioxide. The molecular solids, as I told you, are molecules that are in the lattice sites. Example, carbon dioxide, water, or glucose and sucrose. The molecules are held together by intermolecular attractive forces. These forces can be dispersion forces, dipole-dipole attractions, or hydrogen bonds. Because the attractive forces are weak, the melting points are very low, below 300 Celsius. In the case of the ionic solids, the ions occupy the lattice sites and they are joined together by electrostatic forces that are non-directional and very, very strong. The coordination number represents the number of close cation and ions interaction in the crystal. The higher the coordination number, the more stable is a solid because it contains lower potential energy. The coordination number depends on the size of the cations and anions. If the the anions are always larger than cations, the number of anions that can surround the cation is limited by the size of the cation. The closer in size the ions are, the higher the coordination number. Here we have an example, cesium chloride. This is a pattern of a structure in ionic compounds. As you can see, it has a cubed hole that is occupied by cesium, the cation cesium, and is surrounded by 4 chlorides. The formula of cesium chloride is 1 by 1 because every atom of every anion of chloride provides only 1/8 of them to the cell. If they are 8, then you have only one anion of chloride in this cell per 1 cation of Celsius. Then the formula is 1 to 1. In the case of rock salts, like sodium chloride, that is an example of this type of structure, the coordination number is 6. You have 4 atoms of the anion per 4 atoms of the cation. As you can see here, you can stop the video and you can study this explanation. The result is that you have 1 cation per 1 anion in the structure. So the formula of this compound is NaCl, 1 cation per 1 anion. In zinc blende structures, that is another type of a structure, the coordination number is 4. In this case, the anion is center cubic, so it provides 4 atoms to every cell, while the cation occupies the tetrahedral whole, so then you have 4 atoms in every cell. As the relationship is 1 to 1, you have the formula is zinc sulfide. Fluoride structure. If fluoride is calcium fluoride, is a compound that is like the pattern of this type of a structure. In this case, the calcium uh, provides 8 atoms to every cell because occupy the tetrahedral holes, while the fluoride uh, is occupies the edges of the cell and also the faces of every side, so provides uh, a 4 cations per 8 anions. So the formula is 1 to 2, and that's why calcium, you have 1 calcium and 2 fluorides in every formula. The antifluoride is the opposite. You have 2 cations per 1 anion. The lattice holes in calcium fluoride are represented here. As you can see, this is a tetrahedral, and inside you have the hole. The non-bonding atomic solids are the noble gases in the solid form. In this case, the atoms are held together by weak dispersion forces. That's why they contain low melting points. The tend to arrange atoms closest packet structure is either hexagonal or cubic. And in this case, they maximizes the attractive forces while minimizes the energy. The metallic atomic solids are, are held together by metallic bonds. What is exactly a metallic bond? Well, it's an attraction between the different cations that made the lattice, and you have surrounding this cation lattice by the valence electron. The melting points can be high or low. Here you have the closest packet crystal structure in metal, example the nickel, and here you have zinc. What is exactly the metallic bond? Let's stop into here. All the cations of the metals are surrounded by the valence electrons that made a cloud of electrons that is free when uh, and they can move freely and very fast. That's why the metals are good conductors of electricity and also of heat. The As you can see, the melting points in the covalent solids are very high, higher than 100 Celsius. And why is that? Because the atoms are attached to their nearest neighbor by covalent bonds. And they do not tend to form closed packet arrangement in the crystal. Because the strength of the covalent bonds, the melting points are very high, and uh, you have here the diamond structure. The diamond structure is made by a tetrahedral geometry where the atoms have orbitals sp3 that you will study in organic chemistry. And they made together a very big molecule that is held together by covalent bonds. The property of diamonds are a very high melting point. They are very rigid. They are very hard. That's why they are used as an abrasive. And is the best conductor of heat. Is a is an electrical insulator and is chemically very non-reactive. In the case of graphite, make planes of hexagons similar to the benzene made of orbitals sp2. Every bond contains a 3 sigma bonds and 1 pi bond. You're going to study this in organic chemistry. The structure is trigonal planar and all the different planes that make the graphites are joined together by dispersion forces. Here you can see that's why they are used as lubricants. They are electrically conductor, they are thermal insulator, and they are non-reactive. Silicates are made of silicon and oxygen. Sometimes aluminum substitutes silicon and make aluminosilicates. They make glass and that are amorphous form. Quartz is colorless, but sometimes they have some color because of impurity they contain. They make a three-dimensional array of silicon covalently bonded of silicon to 4 oxygen, making this something like this. They melt at around 1,600 Celsius degree and they are very hard. Micas are another kind of a structure that contains uh, different types of cations, as you can see here, and these are mainly two-dimensional arrays of silicon bonded to oxygen, making hexagonal arrangement of atoms. They make heats, and they are chemically stable, thermal and electrical insulator. The band theory is a theory that tries to explain how metals conduct electricity while the non-metal don't conduct it. And it depends on one part that is called as energy band. That is the result of the molecular orbitals that we have. As you can see, in the band theory explained that we can have a band of bonding molecular orbitals that is called valence band, and a band of antibonding molecular orbitals that is called conduction band. The closer or the higher that can be this band produce a conductor, a semiconductor, or an insulator, as you can see here. The semiconductors are the metalloids that are between the metals and the non-metal, while the covalent molecular compounds are insulator because they have a very large gap between the valence band and the conduction band. Here in the metals, the energy gap is too small, so the valence band can go into the conduction band and